According to a study done by the University of Birmingham in mid-2019, researchers discovered that 2% of the entire world's population uses contact lenses. I'm sure everyone is familiar with what a contact lens is, but for the 98% who aren't familiar with the application of these items, let me refresh your mind. You buy a small box that houses an even smaller plastic container, or sometimes you could buy the plastic container itself. This container is simply the housing for the lens and its cleaning solution. But those same researchers at Birmingham found out these handy containers are being thrown away in heaps and tons. People who get an upgraded prescription receive a new package and have no use for their old one. This results in 58.4 million tons of plastic waste. This needs to be disposed of immediately. Introducing Hexa Robotics, a team of hardworking students at Conestoga College with a vision to change this very same garbage into our very own creativity. With the number of human beings on Earth growing day by day, so is the number of people who are using contact lenses, and the number of people who are getting them replaced. We are proposing a designed process to shred, sanitize, and mold this plastic waste into our very own Hexa blocks, a fun block for children to build whatever they can imagine. Before we dive into each of the stations, here's an overview of the entire cell. It begins with the cleaning station, where plastic contact cases are processed, then extruded into uniform plastic pellets. Once we have these pellets, we move them into the injection molding machine, where the Hexa blocks will be formed. After the blocks are formed, they move to the quality station, where they are oriented, inspected by our very own vision system. From here on, they are packaged and sent out to our customers. Each station has its very own HMI screen that can run on auto mode as well as manual. There is also a main HMI screen for monitoring, troubleshooting, and debugging. Our process begins with the intake into our cell. Intake for our process begins when the blister pack packaging is delivered from all around the world. They will be received and loaded into carrying devices by our shipping department. This will allow for loading into our cell using a forklift. The forklift driver can dump the contents of the carrying devices directly into the shredder, and the process will commence from there. In this visualization, the interlock doors are wide open, which would ensure that the cell does not enter any sort of cycling mode, and ultimately can guarantee us the safety of our drivers. Once all the blister packs have been safely loaded into the shredder, our process can commence, but only after the interlock doors have been closed. The sequence for the cleaning is as follows. The first machine is a shredder. This breaks down the material once it has been loaded by our forklift driver. We then use a friction washing unit to tumble and clean the shredded material. This will be directly deposited into a float sink tank to separate contaminants from pure plastic waste. The next important task will be removing excess water from the waste. This will be accomplished by squeezing the material using a combination of an expanding auger and a shrinking tumbler form. We then deliver these sanitized plastic scrap cutlets to our extrusion machine, the final capstone to the cleaning process. Here, color dye is mixed into the molten plastic before extrusion. The extruded filament is then pelletized by a rotating fan blade, and we now have the final form of the material required to mold our Hexa blocks. A camera will be used for quality and will be top mounted to the shrouding of this conveyor belt. This conveyor belt is directly after the extrusion process, and it will monitor pellet color and is directly linked to the level of dye injection in our extrusion process. Finally, we must transfer the plastic pellets to the hopper on top of our injection molding machine. We do this with the assistance of an air compression unit. Here we will see one of our major system improvements from design phase. Previously in our design binder, we did not have a 90-degree turn in this conveyor belt. With this added, we were able to save a large portion of floor space and shrink overall travel time using conveyor belts. Following our pellets into the injection molding process will take us to our injection molding machine, capable of 12,000 hexablocks per 1 hour. The plastic granules are consistently fed into the IMM chamber, where they are pushed forward by a rotating screw head. The plastic will re-enter a molten state, and the decreasing chamber diameter will increase the system pressure. To inject the molten plastic into the mold, the screw is then pushed forward using hydraulic power, and the material is forced to leave the chamber through its nozzle. Then, the plastic will get injected into a 3-part mold, where our hexa blocks are formed. These molded bricks are cooled and sent on a conveyor belt as soon as possible, straight to quality inspection and processing. The quality cell consists of multiple conveyor belts to move the newly formed blocks around the station. Here, there's a part orienting bin feeder, a vision system to monitor the quality of the blocks, and a Delta robot to remove parts rejected by the vision system software. Quality has a large hopper for making large portions easy to handle. This helps store the blocks while they accumulate while the packaging boxes are being created. Newly formed hexa blocks are dropped from the injection molding machine straight onto a conveyor that transports into the orienting bin feeder. Parts will then run through a series of tooling where they are properly oriented for the vision system to view and process. As each hexa block is passed by the Cognex vision system, they are analyzed by the Cognex program. That program can be seen here. This program checks that each part is within the acceptable color range, size, and has a proper top pattern. If the part passes the quality check, it will continue down the conveyor belt to the sorting bin. However, if a part does not meet all these quality requirements, it will be tagged as a reject. After the vision system has determined that a part is a reject, it will be removed from the sorting station to the reject conveyor belt via an ABB IRB 360 Delta robot mounted on a solid frame. The reject conveyor will then transport the part all the way down the conveyor belt to a bin where the parts will be reintegrated into the shredder to be reprocessed as scrap. The parts that have not been rejected are transferred into a separate hopper to await packaging. When a box is present in the packaging station, the intermediary waiting area bin will open and automatically fill the cardboard box presented by packaging. This very same bin will be refilled by the quality system. This third major process of our cell includes 2 robots, 2 taping stations, and a filling station. We utilize a FANUC M20IA as our packaging robot, and a Cartesian gantry robot for palletization. It is used to unfold and tape the bottom of the boxes. This robot can make 8 boxes a minute. The first station, the FANUC M20IA box builder robot, picks flattened boxes from carton frames using vacuum grippers, end-of-arm tools, and a rotary actuator that will then shape the box to form. The erected box is then brought to the bedding frame, which folds both bottom box envelopes, and the robot continues to the bottom taping station, which will seal the bottom of the box. The second process of our packaging cell is actually filling the hexa blocks into the designated shipping containers. This is a joint operation with the quality process. Once the box is filled, it will be moved through the conveyor belts to the top taping station. A sensor at the start of the conveyor belt will detect when the box enters so the cycle can start. The box will leave the station sealed completely. Finally, the last function of the packaging station, the Cartesian palletization station. The box continues to move forward after it has been completely taped and sealed until reaching a set of sensors located at the end of a conveyor belt, at which point the conveyor belt will stop. The Cartesian robot will be notified of the location of the box, and it will come to pick up the box using a set of vacuum grippers. It will then place it onto a pallet. Once the pallet is completely loaded, an operator will carry the pallet using a forklift, at which point it will leave the cell to go back towards shipping and receiving.